All right, the purpose of this video is to try and introduce blackbody radiation with a demonstration and a PhET, and we can go over the math in another video. What you can see up in front here, this thing is a variable transformer. If you look carefully, you might notice the numbers. Hopefully it's just barely visible on the screen, but notice that goes from 0 to 100. And a light bulb is plugged into here. So what do these numbers mean? It means it goes from 0% of maximum to 100% of maximum. So basically, it turns an electric socket into a variable electric socket. So we can adjust the voltage basically from 0 volts RMS to 120 volts RMS. And I've just got a light bulb plugged into here. It's an old school light bulb. It's not an LED like you kids are probably used to these days. But there's basically a chunk of metal in there. And as I turn this on, you'll see the metal start to warm up and it glows, right? And so hopefully, let's make sure you can actually see that. You can. And while I'm going to kill this front light so you can see the bulb without any, and let's just slowly ramp this up. Okay, so it's basically at 0% right now, and I'm going to start ramping it up. Notice that's a nice red color. So this one's a little tricky if you're colorblind. I apologize about that. Let's keep going. More voltage. It starts to look kind of orangish or maybe even orangish yellow. Now it's starting to look quite yellow. And notice it's getting brighter. Now it's looking even more yellow, getting brighter. And now we're going to get, where are we? We're about a third of the way up. Now it's definitely like, it's almost like a whitish yellow. And now we're up to about 50% of full brightness, and it's starting to get whiter and whiter and whiter, and it's getting ridiculously bright. But we can see here, now it's very white compared to when we started. Where we saw this very deep red way at the beginning. Right, so we do see this light transitioning from a very red color to extremely high intensity white color. And that's now full on, very white. Okay, I'm going to turn that off before I forget. Oh, it looks like I was almost burning something. I don't want to know what I was doing there. Let's worry about that some other time. All right, let's go to a screen share real quick. Let's go to screen 1. All right. And so hopefully you can see me adjust. What I'm going to do now is I'm going to start from a very low temperature. This is sort of the same thing. The idea is if we increase the voltage applied to the filament, more and more electricity ran through the filament and it got hotter. Okay, so as it gets more and more hot, somewhere right around here, and some things to note, maybe I'll annotate something. This up here is talking about the amount of red, green, and blue light emitted by the light bulb. And this is the net color seen by your eye. When we add red and green together, you're going to get yellow. When we add red, green, and blue together in equal amounts, you get white. Okay, so that's kind of that. And then over here, you can see there's a temperature gauge. And then I'm going to ramp this up. So that's what's going on in this simulation. Let me stop those annotations and just start rocking here. Okay, so again, we'll start from off. And as we warm this thing up, at some point, I'll have you notice there's some small amount of red light right down in here. Right down here. And that's very, so this curve is relating to the amount of light emitted. It relates to the brightness of the bulb, which relates to power. And here we're doing a power density with these unusual units. And so obviously the amount of power emitted by the light bulb depends on the wavelength. So that's why it's per micron here. So it's which wavelengths are emitting that light. All right, so notice the area under the curve would be power density, megawatts per meter squared, right? And so that's averaged over all the different wavelengths. Okay, so let's get rid of this, and this. All right, so I'm going to one more time. Start from 0. Okay, we're heating up the bulb. And right around in here, we start to see, whoops, right about, I think it was right in here, we saw a nice red color for the bulb. Now, you can't really see it that well. Whoops, wrong one. If I zoom in on the scale, you could see the light bulb is emitting in the red, but it's very dim. And this matches what we saw with the light bulb. It was very dim red at the start. I'm going to go back to our standard scale. So now this is out of 100. As I heat this up, the color becomes more orangish, more yellowish. And we start to see the overall curve get larger and larger. By that I mean this peak is getting higher and higher, so there's more power emitted by the light bulb. Okay, undo, undo, undo. All right, and then let's keep heating it up. As we get hotter and hotter, look at the color. It's getting whiter and whiter. So notice white hot corresponds to a higher temperature than red hot. We could keep going, right? And notice if we get to the sun's temperature, the sun is emitting a lot of red, green, and blue light. I wonder why our eyes adapted to observe that. And notice you might be saying, wait, I thought the sun was at millions of degrees. And notice this temperature is 6,000 Kelvin. The surface temperature of the sun is about 6,000. And yes, if you're wondering, this does relate to the sigma A E T to the 4th law that we learned in chapter 18, I think it was, or something like that. This was the power radiated. And so, right, that depends on the surface temperature, the area of the sun, the emissivity of the sun, and this Stefan Boltzmann constant. All right. And if we keep heating this up, right, eventually it gets so tall we can't see it on the scale, but we can actually get to blue hot. Right? So blue hot is hotter than red hot. Now, if you're in theater or in movie production, right, you'll often hear about blue being cool and red being hot. That's different. That's a vibe thing. That's not what we're talking about here. But if you talk about more red and more blue in film, things are a little bit different. You could research that. This is about the blackbody spectrum. All right. And so while I've got this up, I have a couple of applications of this. What we see here is that the color of the light correlates to temperature, right? And so if I go to, I think it's this one here, you may see, and now this is just Wikipedia. Oh, and let me get rid of these annotations really quick. Clear all, okay. You'll see different resources will give different temperatures for red hot and white hot, etc. So, different blacksmiths may have a different meaning for red hot. But we do see, in this case, a parameter is used to look at the light emitted by something, and you could measure the temperature associated with it. Oh, there's Stefan. Oh, you probably recognize that equation. Great. And whoops. Oh, that's me right now. That's very meta. I think we could stop this video now. Oh my gosh. I'm going to talk about the math of this in a separate video.